Hello, this is Vasudev Shyam,
This is Evan Coleman.
and we're here to talk about our work on conformal boundary conditions from Cutoff AdS3. We approach cutoff holography via the TT bar deformation. There are many routes to get to this interesting theory, and it relates to integrable field theories, to ghost-free massive gravity, coupling CFTs to random geometry, and so on. But our focus will really be to see this deformed theory as the one that lives on a finite Dirichlet cutoff surface in AdS3. We'll explain that through the course of this talk. The TT bar flow is defined by the following differential equation. It's an iterative deformation where we define a one-parameter family of theories that stem from what we call an undeformed theory. And in the case of interest, this undeformed theory will be a conformal field theory. And at every step of this deformation, we add the following quadratic operator constructed from the stress tensor. Now, we go back to cutoff holography and what exactly we mean by it. In most calculations of physical observables in holography, there's the issue of UV divergences to deal with on the field theory side, which are then mapped to IR divergences or large volume divergences in the gravity side. And normally, when calculations of quantities such as two-point functions, entanglement, entropy, etc. are done through the bulk, we usually take the boundary to be a surface very close to the asymptotic boundary, and then eventually take this regulator epsilon to 0. As an example, when we're computing the von Neumann entropy of a region A in a two-dimensional holographic conformal field theory, the setup is described in this picture here. What we do in the bulk is consider a geodesic, which is a minimal surface, of codimension 2, anchored on the entangling surface, which is the union of the 2 points that demarcate the region A. In order for this length, which would otherwise be the area of this codimension surface in higher dimensions, to be finite, one would have to consider a surface arbitrarily close to the asymptotic boundary in order to obtain a finite result, because otherwise the geodesic would naively have infinite length. And this divergence in the length maps onto the divergence on the conformal field theory side of the entanglement entropy, which we then regulate with the cutoff epsilon. The context we're interested in is the one where epsilon isn't necessarily small. For many questions of interest in quantum gravity, we would like to understand how to move into the bulk. In particular, it would be interesting to understand what sort of quantum field theory is due to the gravitational physics of some finite spacetime volume. And this is what Legault, Messier, and Verlinde sorted out in the AdS3 case, where they proposed that the dual description to gravity in some finite region that is bounded by this cutoff surface at R sub c, as depicted here, is described by the TT bar deformation of the conformal field theory that would have dwelled at the asymptotic boundary. The deformation parameter is related to the radius at which the cutoff surface sits. In this context, one would expect that the entanglement entropy would just be finite were the holographic entanglement entropy prescription to generalize. And indeed, calculations that have been done in the past couple of years show that this is the case. The length of a geodesic that runs between two boundary points, the boundary where a finite radius would have to be finite, and a replicatric calculation of the entanglement entropy of the boundary theory supports this. It gives us the same result. So this already tells us that these TT bar deformed CFTs are peculiar in that their UV properties are unlike what you would expect for any other quantum field theory. So if we just use the entanglement entropy as a probe of some of the short distance behavior, we see that it is capped off, that it just goes to 0 at very small r here, where r is the radius of the sphere that we're doing this calculation on, whereas for CFT, it would have diverged. Another very interesting quantity is the spectrum of a theory that's put on a cylinder. This was historically one of the first quantities to have been computed in the general TT-bar deformed quantum field theory, in fact. And in the work cited, what these authors showed was that the energy levels are deformed level by level, and that the deformation is dictated by this Berger's equation. In the analogy, the viscosity would be set to 0, and the energy levels, the energy eigenvalues, would be related to the fluid velocity, the Berger's equation. So if we take the initial condition for this flow to be that of a conformal field theory, which would then tell us that we should plug in the following expression involving the conformal weights and central charge, what we find is the solution of this form where we see that there are two branches. And the behavior of the theory with either of these signs is different. So if we pick the minus sign, then we find that there's a square root singularity at some energy level. And beyond that, the energy levels go complex. Whereas if we pick the plus sign, then at very high energies, it looks like this theory exhibits Hagedorn-like behavior and is perhaps related to something like string theory. Note that the level at which the energies hit the square root singularity is related to the deformation parameter mu, which is in keeping with our intuition that mu sets the cutoff scale. This is a picture that we borrow from the paper of Megomez and Verlinde that depicts the truncation of the spectrum for the sign where we would hit this singularity. You should also note that this is the sign that they focused on and showed was related to semi-classical gravity in AdS3. So this peculiar feature of the spectrum has to be contended with if we're interested in holography. In the bulk, these energies correspond to the quasi-local energy of a BTZ black hole in AdS3 with the Dirichlet wall. So we identify the mass and spin of the black hole as we would in the conventional AdS-CFT, and find that with the sign that hits the square root singularity of the deformation parameter, there's agreement between the energy levels and the quasi-local energy. Also, from the point of view of the bulk, what happens when the square root singularity is approached is that the cutoff surface hugs the horizon of the BTZ black hole. Past that point, it doesn't really make sense to call the quasi-local energy that we were computing an energy, because light cones are flipped, and what was once a time-like direction becomes space-like, and so too with the Killing vectors. Now, the flow itself that the TT-bar deformation defines has a gravity dual interpretation, and that is the radial development of these surfaces into the bulk. Semi-classically, this tells us that the TT-bar flow equation at large C can be mapped to the radial Hamiltonian constraint equation in the bulk. This is accomplished through a change of variables that relates the expectation value of the stress tensor to the momentum conjugate to a metric adapted onto this constant radius surface. We would be interested in generalizing this beyond the semi-classical limit in the bulk. Particularly, we want to understand what happens when C is finite. And so both on the TT-bar side, where we need to understand the flow equation at finite C, and on the gravity side, where we would need to replace this radial constraint equation with its quantum generalization, which is the Wheeler-DeWitt equation. And in order for us to do this in a tractable way, we will focus on the case where the boundary slices are tori. On the field theory side, the quantity of interest will be the torus partition function. And this is just the partition sum where we take the deformed energy levels from a few slides before, and then compute the following sum with p sub n being the spatial momenta and tau 1 and tau 2 being the real and imaginary parts of the torus modulus. It's been shown by Datta and collaborators that this quantity is modular invariant if the deformation parameter lambda transforms like the imaginary part of the torus modulus. And we do have a flow equation for this quantity, which doesn't rely on the large C limit or anything of the sort, and is a simple partial differential equation. In order to understand what this could map to in the bulk, we would first have to use a slightly different method of defining the partition function of the TT bar deformed CFT. So far, we've been using an implicit definition that takes it to be the solution of a flow equation, whereas there exists a definition with the following integral kernel that you can use to define it in and of itself, so to speak, provided one is able to do this functional integral over field binds or frame fields E. And it was shown by Tolley in a paper from last year that the action that sits in the exponent is actually that of ghost-free massive gravity in 2 dimensions. So one way to look at this is that it's the result of coupling your CFD or undeformed theory to ghost-free massive gravity. But also, thanks to Friedel, we know that this formula allows us to take solutions to the conformal Ward identity, in other words, to the equation that tells us that the trace of the stress tensor in the undeformed theory is given by the Ricci scalar, to solutions of the Wheeler-DeWitt equation in gravity with negative cosmological constant in 3 dimensions. So this is an identity that the functional integral kernel satisfies. Moreover, this kernel definition can be seen to give us the TT bar flow equation that we were using to define the theory in all the slides previously. So now I'll turn it over to Evan.
So the Wheeler-DeWitt equation that shows up when you study the curved space, most generic possible analog of the TT bar deformation in the prior slide, because it involves functional differential equations, we would like to see whether we could simplify it by constraining our system somehow. So on the torus, we can first focus on a description via gravity in constant mean curvature gauge in 3 dimensions. In 3-dimensional Euclidean gravity, the constant mean curvature Hamiltonian constraint is a global constraint equation of the following form. And you'll note that quantization will give us just a single partial differential equation. The momenta with respect to tau become derivatives with respect to tau, and t would become a derivative with respect to v. So that reduces to an equation which no longer involves functional derivatives. It trades them for partial derivatives, but in particular is not a mini superspace approximation of the functional derivative formulation of the problem. So in a very similar spirit, we can define this radial wave function psi on the torus if we introduce a volume factor v, which has the following dependence on mu, the dimensionful TT bar parameter, lambda, the dimensionless TT bar parameter, and tau 2, the imaginary part of the torus modulus. The 4 pi squared is just a normalization factor, but the point is that we have to include tau 2 for v to have the correct transformation properties under a modular transform. We need mu to bring in dimensions of length squared, and we need lambda to derive a useful connection to the flow equation before. So if we write psi as a particular factor multiplying the partition function, we can derive a kernel representation of this object that looks like some sort of smearing over modular parameters of the original conformal field theory partition function. And in other work, recent work by Belin, Lefkowitz, and Sadosi, it was argued that such an object encodes the wave functions of path integral states in the conformal field theory. I refer you to that work for more details, but this is an object that has been studied in great detail in the literature. So when we now write our flow equation in terms of this psi, we find that we derive simply the Wheeler-DeWitt equation of 3D gravity in a torus universe, but starting from a 2D theory. So this is where we derive the analogy with AdS3 with a Dirichlet cutoff. You see that the torus universe just simply gets truncated, and the radial wave function is defined at the locus of truncation. Note here that T is quantized. It becomes the momentum conjugate to V, so it takes the form of a derivative with respect to V, and that's critical to removing the first order derivative term that appears in the differential equation for the partition function, the deformed partition function, Z of V in tau. At this level, it's worth commenting that both signs are quote-unquote holographic. In the typical vanilla TT bar story, there's a difference between the descriptions of the system when mu is positive versus when mu is negative. Depending on conventions, one is typically characterized as the good sign, meaning that it has a well-defined spectrum for all values and a Hagedorn density of states at high energies, or the sign is bad. This is referred to as the holographic sign that has the Dirichlet cutoff and the complexification of the energy levels at some characteristic energy scale. At this level, none of our procedure cares about the sign of V. The partial differential equation that I showed in the prior slide is quadratic in V, and there's no effect if you swap the sign of V in this expression at the level of the differential operator acting on psi. It happens that the negative sign of mu will dominate in the semi-classical limit in the analysis that we perform, or that is generally performed in this context. But that's a detail that we'll relegate to the literature in this talk. The point is that we can consider both signs freely. Nothing that we do depends on choosing a particular sign of mu. What we'll be considering in this context is, given the Dirichlet story, whether we can change boundary conditions in some sensible way, and what happens to the partition function when we do this. So what do we focus on? We care about implementing polarized boundary conditions, which define a Lagrangian submanifold in the phase space. In other words, there is some symplectic potential omega, which is an integral over a symplectic form over the boundary that we specify must vanish under particular conditions. So, for example, how this works in Dirichlet boundary conditions is we specify the metric G at some cutoff surface, and then the conjugate momentum pi, which is just the functional variation of the action with respect to Gij. It's curious that we can derive a particular relation between systems with Dirichlet boundary conditions and systems with so-called conformal boundary conditions. These are boundary conditions where we fix the conformal part of the metric, which we call Gij bar, and the trace of the extrinsic curvature at the boundary. It's worth noting that this T, trace K, is often referred to as the York curvature time. And in this picture, the corresponding Lagrangian submanifold can be specified by Gij bar and V, and then the corresponding conjugate variables sigma ij and t. In order to change boundary conditions, we need to perform a canonical transformation on the phase space. In other words, moving from a Lagrangian submanifold that specifies Dirichlet boundary conditions to one which specifies conformal boundary conditions requires some change in the action functional, which happens in this case to be generated by V times T. When the bulk is three-dimensional, V times T is exactly the right term to change the boundary action from one corresponding to Dirichlet boundary conditions, the so-called Gibbons-Hawking-York term, to the one that's appropriate for conformal boundary conditions. The result is that holographically, we can imagine transitioning from Dirichlet boundary conditions to conformal boundary conditions by performing nothing more than a Legendre transform of the original little psi and z. This gives us a new radial wave function in terms of the York curvature time t, which we call big psi, and a new partition function which depends on t, which we call gamma. we can derive the corresponding radial constraint equation that psi now satisfies. And in fact, it just comes from quantizing the Hamiltonian constraint, except now V becomes an operator that relates to T as a partial derivative. So this defines a new flow on the space of 2D quantum field theories where the effective action, gamma, is Legendre transformed in a straightforward way and satisfies the following flow equation. One can furthermore identify from the kernel description shown previously that this flow is solved by a new kernel description, which is slightly complicated and a little bit more difficult to interpret. For more details on that, I refer you to our paper. It's worth asking whether there's a concrete notion of energy in this system, whether we can study the thermodynamics, and whether changing boundary conditions has a sensible effect on the thermodynamics. So what we could try to do is just take an ansatz to solve the differential equation, which takes the form a sum over energy levels with some energy conjugate to tau2, the effective inverse temperature, and some angular momentum contribution, which we expect to be left unaffected from the structure of the kernel. The resulting differential equation that we would find, given this ansatz for this frac E of T, unfortunately is nonlinear in second order, so it's not very tractable to study analytically. But we can study the thermodynamics in perturbative regimes. So for example, we can consider the low temperature or large tau2 limit and compute thermodynamic quantities for the ground state. This ends up being tractable, and what we find is that there is a square root, an interesting square root contribution to Z that we can then convert basically into a description of gamma by applying the Hamilton-Jacobi equations, which allow you to solve for the expectation value of V as a function of T. Then, if we simply plug into gamma, we find a value for this frac E, which looks rather involved and complicated. But one can study its properties and show that it's well behaved. If one picks T over root lambda within certain physical bounds, it will be well behaved for arbitrary C. So as long as our parametrization of the flow is valid, there won't be any specification of the theory which removes the ground state. This is characteristically different from the case where we had a Dirichlet cutoff. One could, in principle, remove the ground state by changing the initial data by a sufficiently large amount. In this case, we can also, from the low temperature expansion, consider the high energy density of states. This is because gamma is constructed out of an integral over V of Z of V, and thus shares the same modular invariance properties as Z of V. In this case, if we take a modular transformation that takes tau2 to 1 over tau2, we can use the low temperature expansion to infer the high energy density of states. And what we show by this particular Laplace transform is that the density of states asymptotically approaches a Cardy description, not the Hagedorn description, which is characteristic of a particular sign of mu in the vanilla case, the standard case in the literature. It's also somewhat interesting to study particular solutions to the differential equation. We do probe some of that behavior, and in particular, because the tau1 and tau2 dependence is unaffected by the Legendre transformation, that remains the 0th order Moss form. And the t dependence is the only thing that changes in this picture, and it takes on a rather complicated form. We do discuss in the paper some details about convergence properties, but this is just to note that we can actually find solutions to the psi flow equation. There are a number of ways forward that we would like to explore with this kind of technology. One is to consider higher genus boundary geometries. We could also focus on an extension to the ds-ds picture that has been recently formulated by Gorbenko, Silverstein, and Taroba. It's worth noting as well that since there is a description of this system as a radial evolution in the bulk, it may be possible to connect this system to the recent results studying the Euclidean path integral that basically formulates our description of radial evolution as dragging a torus through some interval and describing the boundary degrees of freedom. Multi-trace operators, moreover, are characterized in AdS CFT as describing holographically multi-particle states in the bulk. This is due to a result by Witt in 2001 that may be of relevance to the problems that we study here. It would be worth developing that connection a bit better. In all, we expect that since TT bar is such a diverse subject area with so many connections to different parts of the physics community, it may be possible that there are other interpretations of the flow that we've produced here. We would like to understand these a bit better. Thank you for your attention.
Thank you all.